What's up, kids? This is Mr. Carlson, C Squared Mathematics. Welcome to another exciting video of trigonometry. 5.8 applications of trig functions. That's what we are going to be doing today. This is the last lesson. The last lesson of trigonometry. Awesome. So, bell work. I have about, I think, 5 questions, like a total of 5 questions that I want to get through. And I'm pretty sure all those questions are on the homework quiz. So again, different numbers, but same process. So pay attention. Homework quiz. Then we're going to go through 5.8. Okay, there's about 3 topics or so that I'm interested in going through in 5.8. A lot of it has to do with some frequency and harmonic modeling, and that's just really music and stuff. So it's really interesting stuff. And then we are done. The next 2 days will just be for review, so you can spend that time preparing for your first trigonometry test this Friday, Unit 1. Let's get started. These are the 3 examples that I want to get through. So go ahead and pause the video if you need to, and we're going to get started on all of them. Okay, so notice that these 3 are very similar, and they're similar in one aspect and one aspect only. You start to see that this is inverse sine of sine, tangent of inverse tangent, sine of inverse sine. So you see sine, sine, tangent, tangent, sine, sine. So when you see something like that, instead of sine and then cosine in the middle, or tangent and then like sine in the middle, when you see sine, sine, tangent, tangent, sine, sine, like when you start seeing that, you're going to be using those formulas, those guidelines for the restrictions from 5.7. Okay, on that very important slide that I told you guys to write down, make sure you have, you're going to be using those and those only. Okay, so I'll remind you that this right here, this interval, okay, if it follows this pattern, inverse sine of x. So if this pattern is like this, inverse sine of x, it will equal x, okay, if it's within this range restriction, negative pi over 2 to pi all over 2. Okay, it needs to follow that restriction there. If it doesn't follow that restriction, then we have to evaluate it. And if the evaluation doesn't work out, then it's undefined. Okay, so let's try to figure what do we have to do here. So the first thing is it within the interval? Is 2 pi all over 3, is this value within that interval? Okay, well, let's find out. If we go to the unit circle, 2 pi all over 3 is all the way over here. Now remember, I need, and when I'm looking at sine, I only really care about the right half of the unit circle. So when I'm looking at sine, I really only care about the right half of the unit circle, this half. So if I'm looking at this right here, 2 pi over 3, is that in the right half right here? No. Okay, so that means it's not within my interval, which means I have to evaluate it. Okay, I have to evaluate it. What does that mean? So I'm going to go back here. I'm going to say not in interval. Okay, and number 2, I need to evaluate it. Now, what does that mean? So it means a couple things. Wow, my pen is not working out so hot today. So give me 1 second. I want to put a smiley face. Okay, fantastic. So evaluate. Now, what does that mean? Well, we know 2 pi all over 3 is 120, okay? And so we're actually going to figure out what this is, okay? So it's radical 3 all over 2. So it's radical 3 all over 2, right? Yes? So radical 3 all over 2, because this is the y coordinate, and we know that y equals sine of theta. So that's what I mean by evaluate it. So that means my next step would be looking at, okay, well, sine, inverse sine of sine of 120 degrees. This equals inverse sine of radical 3 all over 2. Okay? Now what this equals, okay, what this equals is sine of theta, which also equals radical 3 all over 2. Here's the thing though, what's theta? Okay? And you may say, well, theta is obviously 120. No, okay? Theta is not 120 because 120 right here is not within my highlighted right half of the unit circle. So I need to find where on the right half of this unit circle is my y-coordinate, sine of theta, also radical 3 all over 2. Okay? And there's only one of them. It's not going to be down here because sine is all negative. Negative y-coordinate, negative y-coordinate, negative y-coordinate. So that means negative sine. So I have to go over here. That's 1/2. No. That's pi over 2, or radical 2 over 2. No. But here I do have something, and it is my y-coordinate. And it is also radical 3 over 2. So what is my angle measure that I'm interested in right here within my interval, the right half of the unit circle? And that angle measure is, of course, pi all over 3. So I'm going to go over here, erase that question mark because we just found it. It is pi all over 3. And it is just that simple. That's all we need to do. Okay, not a lot of confusing things. We just need to make sure, okay, is it within the interval? No. All right, then let's try to evaluate the parentheses, see where on the unit circle does it give me the exact same value. If it does give me the exact same value. If it didn't give you the same value, well then it's not defined. But it did give me the same value, so boom. Okay? So this one right here is tangents. Now remember, go back to that slide. So this is going to look like this. If we take tangent of inverse tangent of some number x, this does equal x if it is in between negative infinity to positive infinity. So this is very, very nice. You know why? Because that means that can go for any freaking number, okay? Any freaking number at all. All numbers exist. You can plug any number in here and tangent will always hit it. What does that mean? That means this number 4, that's my answer, 4. And if I literally went to Desmos and plugged it in just to double check because you don't believe me, I can type in tangent of tangent inverse of 4, and I get 4. Okay? That's what I get. Now I could do the exact same thing here, inverse sine of 2 pi over 3. So inverse sine of sine and then 2 pi all over 3. Now you're saying that doesn't look right, Mr. Carlson, because it's in degrees, I'm pretty sure. Yeah, so I need to change it to radians. Okay? And that doesn't look right either because I messed up right here. So let me go back. Now divide by 3. Okay? Perfect. Now, what does that give me? Well, if I typed in, hopefully this works. If I typed in square root of 3 and then divide by 2, I definitely don't get the same thing. So what is going on here? Oh, okay, I see. I messed up. So yes, this is radical 3 over 2, but that's not what I wanted to find. What I wanted to find in the first example was this. So pi all over 3. And so yes, if I change it to pi and then divide by 3, I do get that answer right here. And so that's why when you say use a calculator, I mean, Desmos doesn't really help you out that much. I believe your TI-36X Pro does give that answer to you, pi all over 3 if you keep in radians, but I'm not certain. Either way, should you be using your calculator? Technically not, because Math Excel is telling you not to use the calculator. I'm teaching you it all by hand. I'm just saying, at least for this example right here, you could double check just in case with Desmos, okay? But when it gets to like the radian measures, pi all over 2 and so forth, all that kind of, or 2 pi all over 3, it gets a little bit too much, I think, for Desmos. Awesome. Okay, so now let's get to the next one. This one's very, very familiar, similar, I guess, than this first one. So I'm going to rewrite it. So this is going to be sine of inverse sine of some number x. It does equal x, but now here, notice, watch, this one's tricky. Notice how this is the inverse of sine, but this is sine of the inverse. So it's flipped. Now still equals x only if it's in a different interval, a different range. What's that range here? -1 to 1. Notice how right here at the beginning, this first one is a different range. This is an angle measure range. This is a side length range. Okay? So this is actually very, very tricky. All right? Now, what makes this tricky is not necessarily just finding that from your slides, okay, from yesterday. What makes it tricky is this. That looks like an angle measure. But in reality, it's not. What is this saying? What this is saying is sine of theta equals 2 pi all over 3. But surely that doesn't make sense because that angle measure of 2 pi all over 3 was the angle measure here. It would be attached to the trig function. But it's not. See, in the first one, this angle measure, 2 pi all over 3, is attached to the trig function. That's how I know it's an angle measure. But this isn't. So you know what that tells me? They're tricking you to think that this is an actual angle measure when in reality, this 2 pi all over 3 is an actual side length. Yes, just like what I did in Desmos a couple of seconds ago. And you can just evaluate 2 pi all over 3 and you get 1.0 something, right? You get that? Or that was pi over 3. Pi over 3 was 1.0 something. So this is very tricky because this is not an angle measure here. This is a side length. That is why I do this. Sine of theta equals this. Because a lot of students get confused and they just automatically read that as a side length and start just doing it this way. No. You have to pay attention. Does the inverse come first, or are you taking the composition of the inverse? In this way, the inverse came first right here, so my range is an angle measure. But here, I'm taking the composition of an inverse, which means my range is not an angle measure, but a side length, which means that is also a side length, 2 pi all over 3. And since that is a side length, I need to evaluate it as such. So the first thing is first, is it within the interval? What interval? Is it within the -1 to 1 interval? Remember, that's the range of sine. You can't go past that. Okay, it does not go past -1 to 1. Is it within this range? So we actually need to plug this into Desmos and get a decimal answer. See if this is an actual decimal that goes between -1 to 1. So let's go to Desmos. Let's type that in. 2 pi divided by 3. Okay. Now, I still need to make sure I am in radians, because if I do it in degrees, actually, I guess it doesn't matter. Yeah, because it's not an angle measure, right? So it doesn't matter. Okay, so it doesn't matter if you're in radians or degrees because it's just an angle measure. My apologies. But we plug in 2 pi all over 3. What is that number? 2.09. 2.09. So I'm going to go back here. This is literally 2.09. So is 2.09 within -1 to 1? No, it's not. So can you evaluate it? Can you even do something like this? Like, can you even take this at all? Can you take the inverse of 2 pi all over 3 if it's not even within that range? No, we would try to evaluate it, but even if we try to evaluate it with the calculator, what do I get? If I plug this in, so sine, and then inverse sine, and then 2 pi, and then all over 3, what do I get? I get an undefined value because it does not fit the original range for sine. So this is undefined. And that is my final answer. Okay, so you will see some of them on the bell work like that. I just want to be, or not the bell work, well, yes, obviously the bell work. The homework quiz. Because I just want to be very forthcoming with you that is how you would go through it. You have to follow the steps. You have to match it with whatever we had on the notes. And then you have to see, okay, is it within interval? Yes. If it's within the interval, it's that answer. Like this one. It was within the interval, so it's that answer. If it's not within the interval, you're going to try to evaluate it. If you can't evaluate it, then it's undefined. In this one, we could evaluate it. Okay, we could definitely evaluate it within the interval. Okay, with here though, we could not. Okay, we could not, and so that's why we had to put undefined. Awesome. So those were probably the trickiest ones. The next slide I have for bell work is easier ones, and by easier ones I mean they're a little bit easier to understand because they're very straightforward. Okay. So the first step when I solve something like this is notice that this is tangent and this is sine. So I'm not going to follow the same interval. I don't even care about the interval on these. When it says this, when it says use a sketch, I don't care about the interval with these at all. Okay? I only care about the interval on the previous slides one when it was like sine, sine, tangent, tangent, and so forth. You're taking the composition of the same function but just the inverse. Here it's completely two different functions, tangent, sine, sine, cosine. So I solve it completely different. How do I solve it completely different? Well, first of all, my first step is to rewrite it. How I like to rewrite this is, again, to help me. Okay, so tangent, okay, of sine of theta equals -7 all over 25. Okay, that's how I like to rewrite it. So I know exactly what is my opposite, -7, and what is my hypotenuse, 25. Because remember, sine is opposite over hypotenuse. So my second step then is to actually build my triangle in the xy plane. But how do I know how to build my triangle in the xy plane if I first don't know which quadrant I'm in? Now remember, inverse of sine, okay, or inverse of sine and even tangent for that matter, okay, inverse of sine and tangent for that matter are both on the right side of the unit circle. So I don't care about the second or third quadrant. I only care about these quadrants. Now I'm going to ask myself one important question. Are you ready? Is sine negative or positive? Sine is negative here, so which quadrant am I in? Am I going to be in the first quadrant where everything is positive, or am I going to be in the fourth quadrant where sine is negative? It should be very obvious that I can't be here. I have to be there where sine is negative. So that brings me to my third and final step to actually build my blown up fourth quadrant. And that's my theta. I don't care about the theta at all. Okay. My opposite is -7, and this is hypotenuse 25. Okay. Now, going through Pythagorean theorem, I know my x value will be 24. I'm not going to show that. Okay. I actually have that memorized too, just because I've done it so many times. But you can go through the Pythagorean theorem if you would like to. So 25 squared equals, and then 7 squared is just 49, and then plus x squared. You'd go through it, find 24. Okay, just the Pythagorean theorem. Now that I have that, I guess this is my final step. What is just tangent? So what is actually tangent of theta? What does that equal? Well, opposite, which is -7, all over adjacent, which is 24. Okay, 24 there. Boom. That is my answer. Okay, that is my answer. Now, could I technically find the degrees for this? Yeah, I could use inverse functions, right? If I wanted to find the degrees, I could find inverse tangent of -7 all over 24. And now I'd find the degrees to actually be 16 point, I think I have here, 26 degrees, roughly, approximately. Negative 16.26 degrees, because it has to be a negative down here. So that's the degrees. But does it really ask for that? No, it doesn't ask for that at all, so it doesn't matter. But I just want to let you know that it's interesting that we could continue on if we wanted. We could find now the cosine, we could find the cotangent given this triangle. We could do all of this stuff if we really, really wanted. Now, it didn't ask us for the inverse here. It only asks us for the original just straight tangent, and that's what it is. This is the tangent right here, okay? That is the tangent. Awesome. Okay, so let's go to the next one. I erased the previous work. Let's go to the next one. Same thing. It's sine and cosine, so that means it's two different things. I'm not going to look at intervals at all. I don't even really care what theta is. So let's start going through this problem, the first step that I usually do is rewrite it. So that means cosine of theta equals 1/2. Okay? Second thing I do is I want to know which quadrant this is in. So I look at cosine, I don't look at sine, I look at cosine, and then I want to say, okay, where is cosine positive? Where's cosine positive? If all I care about is the first two quadrants, so all students, if all I care about is the first two quadrants, cosine is the one I'm interested in, not sine. Cosine is where I'm going to build this triangle at. So which one gives cosine a positive side length? Not the second quadrant, that's only sine. I'm interested in cosine being a positive 1/2, so it needs to be right here in the first quadrant. So that is my third step. I'm going to blow up my first quadrant. I make my triangle, my theta measure that I don't care about. And now this is 1/2, which means it is adjacent over hypotenuse, which of course, this should be very, very happy indeed to you because this is just a special right triangle, which means my next one is radical 3. You should have that memorized. If you really need to do Pythagorean theorem, you can, but I'm telling you, it is straight up just radical 3. Okay? Which means my fourth and final step is going to be now looking at sine of theta. That's what it is, sine of theta. Okay, what is that? What does that equal? Okay, so opposite, which is radical 3, all over adjacent, which is 2. And of course, if I wanted to find my angle measure, that is just pi all over 3 because I know my unit circle well enough. But I don't really care about that. I could find that if I wanted to. This is really my actual answer. And of course, because certain students really like seeing them, my unicorn. A little angry, kind of upset, you know. Here's his ear. That looks more like an earring than an ear, I think. But whatever. So that is how I do that question. I hope that makes sense. I hope that now you're adequately prepared for the homework quiz, or you feel prepared, for the homework quiz. So I'm going to erase, and you're going to get started. Okay, we are going to do 5.8 application of trig functions afterwards. I think it's rather a fun lesson. It's very applicable. Mathematics is really interesting. You all have 25 minutes, 5 questions, open notes, of course. Please, please, please use your unit circle. Use this thing. Use the trig table common elements. Use your notes. Make sure you're taking good notes. If you have any questions, if you want to review answers, or if you want to send any partial credit requests my way, then do that, please. Do that so that I can help you out during your quiz. Okay? Awesome. After that, you're going to get started here. How's trigonometry used in application? Well, it's a myriad of different applications. Okay, that's the essential question for today. Make sure you're writing it down. It's a myriad of different applications, to say the least. Okay, we're only going to cover a couple of them. So yeah, it's. I love trigonometry. Like I said, it's my favorite math class. It's amazing, and I really, really wish that we were on campus because we would have an amazing music and sine wave activity that we would go through, and that's just unfortunate that we can't. So, all right, how can I solve basic trigonometric functions in various application questions? So the first application question we have is very basic. Very basic. It basically is just solving the right triangle, which means finding all the missing side lengths, all the missing angle measures and everything. I want to solve the whole freaking thing. There's 6 parts, which means there's six total things I need to find. Some of them are given to me and some of them are not. So there's 3 side lengths and then 3 angle measures. So whatever's not given to me, I need to find. So I'm given this picture right here, and it just straight up says, solve for it. Find what it is. Okay. And this is rather interesting. Okay, it just gives us this triangle, no other theta at all, because I need to find all the theta measures, and it just gives me that it's 30 feet up in the air. Okay. And then it also gives me that this is 65 feet of rope. So how can I find how long that is If I wanted to find how long it is, what's the angle measure, and so forth. I can do this. So let's just say this is theta. Let's just say A is theta, okay? So I can go over here, my first step, and you can solve this however you want. You don't need to solve it the way I do it. There's many ways to solve this. But how I solved it was I did sine of theta, so that is just, straight up A. So sine of theta, I want to find what A is, essentially, okay? This equals opposite, 30, and then hypotenuse. Okay, that's why I'm using sine, because 30 all over hypotenuse, which is 65. Now, how do I do this? This is very simple. It just turns into an inverse sine function. So of 30 all over 65, and this will equal theta. Yeah. That will equal theta. Okay? So then what is theta? Well, theta, when I plug this into the calculator, I get a certain number. So let's go to decimals, find that out, make sure we are in, let's do degrees. Let's keep it in degrees. Okay? So let's do inverse sine. And then I want to do 30 all over 65. So that is, I think, in radians. I'm going to go back and change it to degrees. And I get 27.49. So 27.49. I'm going to go back here. So this is 27.49 degrees. So this technically equals my A value. Okay, my A angle. Awesome. So I have one down. Great. Now the next thing that I would do is, now that I have another angle down, is I'm going to find B, because it's very easy. All I have to do is take 90 degrees minus what I just found. Okay? 90 degrees minus what I just found. Remember, you could take 180 minus 90 minus this, but it doesn't really matter because 180 minus 90 is still 90. And then you still have to do this. Okay? So that's why it's easier just to take 90 degrees minus this. When I solve this on the calculator, you guys can do it yourself at 62.51. That is how I would get B. Again, if I really wanted to find it on the calculator, all I would have to do is just, let's just say I label this A equals, and then I can just take 90 minus A, and then boom, that is how I get that answer. And that takes the whole thing. And so I know I have the strongest answer. It's not rounded at all or anything. So that takes the whole thing, not rounded, and gives me an awesome answer. So that's what I would recommend that you guys do. Now, my third thing that I need to find is my last side length. So this is 3. I need to find the last side length. I found A, I found B. I need to find my B side length. And that is a straight up Pythagorean theorem, guys. B squared plus what's 30 squared? We're going to find out equals, and then 65 squared. Okay, this is B squared equals, and then this 65 squared is 4,225 minus 30 squared is pretty easy, 900. When I subtract this, I get B squared equals, and then I get, and I'm going to make sure I have the radical on each side. But this right here, when it simplifies, I get 3,325. Okay? Now, of course, I can break this down if I wanted to, and you can, like, if you wanted to. This actually does break down to 5 times radical 133, but it doesn't really matter. Most of the time, Math Excel is going to ask you for the decimal, which means if you want to just straight up plug that into Desmos, then you can, but my actual answer is 57.66 feet, roughly. Okay, so that is B. So awesome, I found my A, I found my B value, my angle measure, and I found my side length B as well. So there you have it. That's how you solve for the whole triangle. Now, one of them, you were already given that this was a 90-degree triangle. You were already given 2 side lengths, and then now you could solve. So that's great. I'm going to move on and leave it as such. A lot of your homework assignments going to be these types of examples. All right, now, next application is what we call bearings. Okay, if you did watch last week's video of Math at Sea, you would see that logarithms are used. A lot of things are actually used when it comes to sailing the deep blue sea. Okay, so logarithms and what we call mathematical bearings. Okay, so three boats travel in different directions. How could you describe with adequate precision, okay, accurate precision, to be redundant, which direction they are going? This is what sailors call bearings, okay? So in trigonometry, in navigation, we use trigonometry by surveying problems. The term bearing is literally being used to specify the location of one point relative to another, okay? So the bearing from O to point P is the accurate angle measured in degrees between ray 0P, okay? Not 0P, OP, so OP. And then the north-south line. So what does this look like? So it looks like something like this. I will always have like an XY axis kind of thing, but not XY axis. I'll have like a compass, north, south, east, west. You know, never eat sour watermelons or never eat sour waffles or whatever. Okay, whatever you want to use to help you remember. So this bearing from O to P is north 40 degrees east. Why? Because you start at north, then you go 40 degrees, and then east. So that means right here, that's the bearing P. Okay, so north 40 degrees east. This one is north 65 degrees west. So you start with north, then you go 65 degrees west, and then you get your terminal side. And then this one is south, and then you go east. So notice how you always start with north or south, and then you always end with east or west. Okay, so you always start with north or south, and then you end with east or west. All right, so keep that in mind. So each bearing has three parts. It has a letter, N or S, the measure of the acute angle, and then another letter, which in this case it's just E or W. And then here's how we write really the bearing. So you'll always have like north or south, some north or south, the number in degrees, and then east or west. Okay, so it'll look something like this: north, south, number in degrees, east, west. Okay, sometimes you have it in radians, but we're going to keep it in degrees for the time being. Okay, so now I'm given this. I want to find the bearing from O to B and the bearing from O to A. How do I find the bearing from O to B and the bearing from O to A? So the bearing from O, the origin, to B. Where's B at? Right here. So that means I would go north, okay, and then west. So this is north, 40 degrees west. Okay? O to A. So O, I would go, this one's a little bit tricky, okay, because I don't have this. I would go north, right? But here's the problem. I don't have this. We need to find this angle. We need this angle from O to A, right? So what is that angle? Well, if this whole thing is 90 degrees, then that means this must be 70 degrees, right? And so that means if I go north and then over 70 degrees east, I get to A. Remember, you need to do north or south first. So north and then 70 degrees, and then I get to east. Okay? Perfect. All right. Let's do these. O to D. Try it. Try it yourself, actually. Try to see if you can get O and then D. Get OD'd. Not really. Don't do that. That's bad. All right. So O to D. Let's see if you got it correctly. Start with origin. Go down because it's south. So I go south. And then I go over how many degrees to get to D? 25. 25 degrees east. O to C. Down. Okay. Down south. So I get south. And I don't have this value right here. What's that value? Well, if this is 75, excuse me, if this is 75, then this must be 15 degrees because that gives me a total of 90 degrees. So that is 15 degrees west. Awesome. Awesome, awesome. So that's the basics of bearings. Let's actually apply it to something. So finding the bearing of a boat. You're gonna have many examples on your homework that are like this, and some of them are very annoying. They're not gonna give you a picture like I'm gonna give you a picture now. So just FYI, you're gonna have to build the picture, okay? But hopefully this will make a lot of sense so you can build a picture yourself. A boat leaves the entrance to a harbor. Okay, so this is probably the origin. So think about that. If it leaves the entrance to the harbor, that's what we call the origin. And travels 25 miles on a bearing northeast. So first of all, which quadrant is that? North and then east. So that means this is going to be in quadrant 2. Okay, so think about that. It's going to be in quadrant 2. I'll probably build some sort of quadrant 2. Now, shows that the captain then turns the boat 90 degrees clockwise. So clockwise is like this, okay? 90 degrees clockwise and travels on 18 miles with a bearing southeast. So now you're basically, this one's hard because you're basically given two different sections, almost two different quadrants right on top of each other. What we want to know is how far the boat is from the harbor entrance, and also what is the bearing of the boat to the harbor entrance. Okay, so this is the picture. Now notice how I said it's almost like two different XY planes on top of each other, because it is. Now here's what I'm going to do, because this is very helpful to us. I'm going to start labeling this. So that's H, my harbor entrance. And then I'm actually going to draw a straight line. I wish I could do a straight line. How about this? I'm going to do my web paint here. Let's do red. Boom. Okay. That is much better. Boom. Okay. I'll keep that just chilling the whole time. All right, so that's my harbor entrance. This is my straight line. Now this is what we call the x-axis, or the east, okay? And this is obviously my y and my north. Now, what do I do here? Okay, well, first of all, the boat's traveling right here. The boat travels 25 miles from a bearing northeast. So this was my second quadrant. But then, this is what gets tricky. It turns 90 degrees clockwise and goes down. And here, of course, is your boat. All right, right there. Now, since it goes down, that's what makes it tricky. Here's what I want to find. A, in blue, how far is the harbor entrance from the boat? How far is the boat from the harbor entrance? So that's A. So let's get started. Well, first of all, if this is 25 miles and this is 18 miles, and it's given to us in the problem, how can I find that? Well, that's just a simple straight up Pythagorean theorem. So what's the distance? Well, the distance squared equals 25 squared and then plus 18 squared. Okay, 25 squared is 625, and then plus 324, and this equals 949. And of course I have d squared, I square root. So that means my d is approximately equal to 30.8 miles. Okay, and of course this is very easy. It's Pythagorean theorem. You can plug that into Desmos real quick and just solve it. So that's why I wanted to solve it like that. Okay, now what is b? Tangent. Why do I want to use tangent? Why do I want to use a trig function in the first place? Because it's asking what is the bearing of the boat, okay? But I need to find what this degree is. That's the problem. Okay, look at this. I need to find what that degree is in order to even solve it. So why do I want to use tangent? Because I'm given opposite 18 and then adjacent 25. So I need to use tangent of theta equals 18 all over 25. In order to find the bearing, I need an angle measure. I need to know this whole thing. That's the thing. Watch. I need to know that whole thing. This whole thing. Yes? So I need the 42 degrees plus something else. I don't know that something else. That's why it's called theta. How do I find theta? Well, you see, kids, if we utilize our knowledge from 5.7, we can find theta. So this is 18 all over 25, and then that will equal my theta. Let's keep it in terms of degrees. I plug that into Desmos exactly how I see it, or my TI-36X Pro, making sure we're in degree mode, and that is going to be theta equals 35.8 degrees. Okay, so that's my theta, but is that my answer? No, it's just that little bit right here. I need this whole piece. Notice my cursor here. I need that whole piece. I can't just have that little bit. I don't care about that little bit. I need this whole thing because that's what it's asking. What is the bearing from the boat to the harbor entrance? So I need the whole angle in order to find the whole bearing. So I need to plus that 42 degrees. And so now what I get is equals 77.8. So that's that whole degree thing right there, which means my final answer, and I'll put it in bright green here, is north 77.8 degrees and then east. That is my final answer. Looks like a little bunny rabbit. It's a unicorn though, for real. All right, so I wanted to find all that. I did. I go north, and I go all over, and then I get to my boat, which is right there. Okay, because this is 77.8 degrees. Perfect. Perfect. Awesome. Okay, so you will have a lot of questions like on your homework concerning this, and these are very difficult because you do have to build. You have to build your questions. So I'm just forewarning you. Be prepared. Okay? Now, let's get rid of that because I don't need that. Now, let's go to my next one, harmonic motion, and then we have frequency and harmonic motion after that, and then we are done. So harmonic motion, what is that? Well, an object that moves on a coordinate axis is what we call in simple harmonic motion if the distance from the origin is given by this. Notice, not using tangent. I'm only using cosine and sine because those are the only ones that matter. Those are the main sine waves. Okay, we can just add sine waves together to make our sound. So the motion has an amplitude of absolute value of A. That shouldn't change. The maximum displacement, this is something that's new here, of the object from its rest position. So our amplitude is now going to be what we call the maximum displacement in its rest position. So I'm going to show you what that means in a little bit. The period of the motion is still 2 pi all over b, but in this case it's 2 pi all over omega. So omega is going to act as our b value here, okay? But it's literally the exact same thing. Obviously, it can't be less than 0 or greater than 0. Well, it has to be greater than 0. It can't be less than 0. That's what it is, yes. It can be less than 0 because if it's less than 0, that doesn't make any sense because it's a real-world application. You can't have negative motion, okay? You can only have positive motion. The period gives the time it takes. Now, here's the interesting thing, guys. Pay very close attention. The period gives the time it takes. The time, which is why we have T, okay? We're looking at time now. It's time it takes to go through one complete cycle. So sometimes you will be asked, like, how long does it take to go through one complete cycle? That is what we call the period, okay? Now think about this, the paddle ball, and I'm going to show you an example like this in a little bit. If I had a paddle ball, I should just buy one just for this case. I actually have a better idea, okay? I have a way better idea. What if you have a tennis ball? It works basically the same. And this is really what harmonic motion is, guys. Whenever you bounce a tennis ball, okay? Whenever you bounce that tennis ball, notice when you bounce it, okay, it stops depending on the force that you exert, okay? And that's more physics, but you can exert a lot of force and it goes screaming high, right? But it always bounces down. Now, why does it just get more like less bouncy? Like, why does it get less bouncy? Is it because of just something wrong with the mathematics? Actually, no, it's because it's just straight up gravity. It doesn't have any force attached to it. That's why you can dribble, and if you dribble, it keeps going over and over and over and over again, right? That is what we call a simple harmonic motion. The maximum displacement is what we call the amplitude. So the amplitude is when I drop it, and then it bounces back, okay? That is what we call the amplitude. Now, it doesn't bounce back the whole way, okay? I would need to actually do more force than what gravity is giving it. In order for it to bounce back, I would need to actually exert a lot more force, not just drop it, okay? That's all physics stuff. Very interesting indeed, but that is beyond the scope of this course. What we are going to be doing is just, like I said, simple harmonic motion. Now, this is also another interesting thing of vibrations on a guitar string. When I pluck my low E string, okay, my low E string, you can actually see it vibrate. Okay, you can actually see it vibrate. If you have a guitar, do it right now. Like, go to your low E, you can see it just vibrate back and forth. Now, the reason why, again, just like the ball, it just kind of stops after a while is because there's no more force exerting on it, correct? But when you keep playing it over and over and over again with like a pick or something, the force keeps going back and forth, back and forth, back and forth. That's why if I really want to go to town on my guitar, I would just bang, go to town with a lot of force. Or if I wanted to be very, very silent, like Beyonce or something like that. Or Taylor Swift's folklore album, I would want to do a little bit more silent and not pluck it as much. Either way, you still have what we call a simple harmonic motion, okay? Let's go through an example. A ball is on a string and is pulled 4 inches. Pulled 4 inches below its rest position. That's like one of those paddle balls. And then released. The period of the motion is 6 seconds. Write an equation. Now, first of all, these are my variables. I always like listing out my variables. D is distance. Okay, so like for my tennis ball over here, the distance it actually travels, right? That's the distance. Time is T, amplitude is A, and then my W would be what we call our B. It's technically our angle measure there, okay? So I'm given this picture. Not always will you have this picture, but this is kind of what it is. You have like a springboard, like it goes back down and so forth. So what we want to do is do this. I want to, in green, kind of trace it. Now, why do I want to trace it? Because I want to find what my function is. The first question we need to ask is this sine or cosine? This should be cosine. Sine looks like this, okay, over here. Sine starts at 0 and then goes up and then down. Cosine starts at 1. Okay, cosine, if I can draw it right here, cosine starts at 1 and goes down and then up. And now this is flipped. This is a flipped cosine graph. So now it's like this. Okay, but still cosine. Okay, it's just flipped, which means since it's flipped, make sure, since it's pulled down, we have to make sure we look at the negative part of it. So let's list out what A, B, P, whatever we need. So A is probably the easiest. I already know I'm going to use cosine. Okay, so what is A? A is 4 inches because I pull it down 4 inches. So it's at its rest position right here, right? Okay, but right now at T sub 0, my hand pulls this down, okay? Pulls it down from almost like its rest position, which is what we call 0. So my A, when it's pulled down 4, that right there is my amplitude, okay? Now, of course, my amplitude A, my amplitude would be 4 inches, but my A value is -4. So my amplitude is 4 inches, yes, because it's the absolute value, but my actual A value that I'm going to put into my equation is -4, okay? I also want to find my period. So what's my period? Well, my period is 2 pi all over omega. Okay, that is what the formula is. Now, do I know my omega? No, it doesn't give me anything indicating my angle measure, the force or whatever that's indicating that. Okay? So I just need to find my period. Well, how do I find my period? I use my graph. So right here, this is cosine, and then it repeats right here at that value. So it repeats at that value, and then it goes, and then it repeats again. So how many values are in between there? 6. Okay, 1, 2, yeah, 1, 2, 3, 4, 5, 6. So t equals 6. Now, some of you may be thinking, well, if you wanted to count it like that, isn't it 7? Because 1, 2, 3, 4, 5, 6, 7. Technically not, because you're not going to release this until after t sub 0. So like technically, it is really confusing. You pull it down at t sub 0 and you let go, and then it's bouncing back and forth. Okay, so yes, this is like the beginning, but it's still t sub 0, and we don't count t sub 0. It's just t sub 6. Right here is where it ends, and then also right here is where it ends. Okay, so we don't count that. That's the beginning. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So our period is 6. Now this is 2 pi, and I don't know omega. But now, since I know my period from my graph, can I find omega? Yes, I can. I can just multiply by such, divide by 6. So omega equals 2 pi all over 6, which equals pi all over 3. So that is my omega. That's my b value. So now that I have all of this, okay, remember it's negative because it's pulled down. Now that I have all this, I can actually start writing my formula. I know it's cosine, so negative 4, because that's my a value, cosine. And then my omega is pi all over 3, and then t. That is my complete formula. Perfect. Wow, this one's a chunky one. Sometimes it happens, that COVID life. All right, let's erase. Let's do this one. Try this one by yourself as much as possible. So go ahead and pause the video if you need to. And try it by yourself. See if you can actually get it yourself. This one's slightly tricky, but basically the same thing. Okay, so the first thing I always want to do is find my a value. So it says the attached object coil string, object is pulled down negative direction 4 centimeters. Okay, so that means it's negative 4. All right, just like before. This is still 2 pi all over omega. Okay, so that means I need to find what my period is. Okay, if the period is 3 seconds, awesome. So it tells me that 3 seconds. So that means 2 pi all over omega. I multiply by omega, divide by 3. So omega equals 2 pi all over 3. So this is my b value, my omega value. And so now I go to my formula for my second step. Now the reason why this is tricky is because technically they didn't say sine or cosine. So this is negative 4 sine of 2 pi all over 3t. Or it could be negative 4 cosine, not sine, of 2 pi all over 3t. Okay, so it could be either one. It just didn't specify. All right, so if you got that right, awesome. You are right on the money. We have just 2 more slides, and then we are solid. Okay, solid for Unit 1. Isn't that crazy? I think it's pretty crazy. All right, so frequency, you start to learn a little bit more about it in physics. So we're not going to touch on it completely here, but we will touch on it just a little bit. So the object in simple harmonic motion is given by this, has a frequency of this. So frequency starts to happen when I look at guitar strings. Okay, guitar strings have that harmonic motion, but also has a frequency. Okay, because it's a note, right? It's so strung up, it has a frequency. Or rubber bands. Think about that, guys. When you pluck a rubber band, how many of you, be honest, you would get like a rubber band, like kind of like stretch it and then just kind of play a little guitar thing? It's kind of like, and then your mom's like, knock that off. All right, I did that all the time. And I really like stretched it out to get like a nice higher sound. I wanted to get a lower sound and everything. And now those aren't really like great sounds, but let me tell you, it's still a frequency. And frequencies are just notes. So technically they are notes. Did I know what the notes were when I was a kid? Absolutely not. But they still helped, and I was still jamming out. And you could do that too. But we could find the frequency of certain notes. And again, if we were doing an activity in class, we would do that. We would find the frequency of certain notes. Okay? So these are the two important formulas. This doesn't really change. We already know that. But now the new thing is the frequency down here. That's the new thing. The frequency is actually the reciprocal of the period. So 1 all over the period. So let's go through this example. An object moves in simple harmonic motion described by the equation as such. So this is nice. They give me the equation, but they're going to ask for certain things. So they're going to ask for find the maximum displacement, find the frequency, and then find the time required for one cycle. Now, what's the time required for one cycle? That's actually the period. Okay, so the period is the time required for one cycle. Awesome. Awesome. So find the maximum displacement. Well, the maximum displacement is the same thing as what we call the amplitude. Okay, don't get that confused. The maximum displacement is the same thing we call amplitude. This equals, just look at my formula that's given to me, 1/2. Okay, so 1/2 is my maximum displacement. Now, technically, it is in inches, okay, because you are pulling it however many inches, right? Yeah, because D is in inches, so that's you're pulling it like the object moves that many like inches back and forth. Frequency. There's two ways to solve it. One way you could solve for the period, and then the second way you could just flip, like solve for the period and then flip, or you can just flip the period formula and solve it that way. I'm going to do it the second way, and the second way is just saying this: my frequency equals my omega all over my 2 pi. So this is just my frequency formula, but it's my period formula flipped. Okay, it's reciprocal. So what's my omega? Well, my omega right here is 2 at the very top. So my B values, so this is 2. This is all over 2 pi. And then the 2's go poofy, and so this is 1 all over pi. And technically, because it's frequency, it is going to be in hertz, right? But you don't need to know that. Math Excel will already have that for you. Okay, but it is 1 all over pi, which means what is my actual time required for one cycle? What does my period actually equal? Well, it's just this flipped. So that means it's pi all over 1, which is the same thing as pi. Okay, and because we're looking at time, technically it's seconds. So pi in seconds, pi seconds, whatever. Seconds for pi? Yes, please. All right, that is it. Okay, that's all I have for you for 5.8. There's no more videos for the rest of the week. I just want you to be reviewing for your test. Okay, 25 questions. It will be 90 minutes, and it's going to be due Friday at 4 p.m. Okay, so let's erase. What do we learn? We learned 3 things mainly: solve a triangle, solve problems using bearings, and then we also learned a lot about harmonic motion. Okay. Now, unfortunately, we're not going to do this awesome activity, but just think about it. It's amazing. I love this little bit of history with modeling music. You can technically model music, and we would have done that on our actual activity. So unfortunately, because of COVID, we can't do that. But I hope that whenever you listen to a song or whatever, whenever you hear your mom screaming at you, whenever you're talking to someone else, you give a newfound appreciation for what you're doing, because what you're doing is literally speaking sine waves. You're speaking sine waves in such a way as to make your voice louder or smaller. Okay, so 5.8 on Math Excel. I hope you enjoyed this unit. I really, really do. I really love trigonometry. It's not my favorite unit. My favorite unit is by far the next one. I love it, but let me tell you, get ready. This is C Squared Mathematics. Be sure to like and subscribe. Peace.